If I get corona, I get corona. At the end of the day, I'm not gonna let it stop me from teaching computer science. I've been waiting for the spring break for a while. For 2 months, I had these lectures planned, 2 or 3 months. I'm just out of here having a good time. I hope you guys know what I was referring to. I was referring to that college student who was saying that partying is much more important for him than coronavirus.
If I get corona, I get corona. At the end of the day, I'm not gonna let it stop me from partying.
Which I'm not sure if you know, but he recently had to apologize for. So he said that, he said sorry, for the comments. He was mostly apologizing for the insensitive comments versus the actions, the partying and the spreading the coronavirus. Okay, so I definitely don't want to defend him. What he did was absolutely. There has to be politically correct phrase here. His actions seemed immature. Oh, perfect. Politically correct phrase. Yeah, so his actions seemed immature, but at the same time, though, that's the most honest answer which you can expect. You catching a person in the middle of doing something bad, and what is he supposed to say? So so many students, what are they supposed to say? If you expected some honest answer, that was the most honest answer. For me personally, he said, what he meant was, coronavirus is not as important as having fun. The coronavirus was exaggerated for him personally, in his opinion, right? It's not that dangerous, and he's just have been planning that trip for so long. Why would I have to postpone that? Why would I have to do anything with it? In his opinion, again, and that was super honest, super honest. And he had to apologize for that. And it's interesting again because in the text he said I apologize for the actions, but the severity of the comments, that was the worst thing. And he just got unlucky, in my opinion. He got on the news, and that was the first thing in that section of the news piece, right? So there were so many people talking about it, but the way he said it, was eye-catching. It was a bold statement. If I get corona, I get corona, and then it just got spread out everywhere. And but again, he was super honest, and there were so many people doing that, but he was unlucky and he got attention. Yeah. I have a question, by the way. So those people who were editing the news, okay, so they know that they shoot for NBC, CBS, that channel. They know that a lot of people will be watching that. They also know that nobody is going to support this guy, right? So nobody's going to support that thing when you say I don't care about the disease which the whole world is going down for. Okay, nobody's going to support that. So if he's 21, if he's partying at the Miami Beach, he's probably drinking. If he's drinking, he's probably 21 years old. Well, let's say he's 21 years old. If he's 21 years old, he's probably senior or junior, which means he's probably graduating soon. And now he got on the news, and he became so popular. Okay? So if people who were editing the news, if the point was to show that there are college students who don't listen, or let's say the government has not, or the colleges, the Miami government did not do good enough job to keep them safe, if that was the point of the news, then they wouldn't have to put his name out there. So the people who were editing, right? My question is, how moral, how sensitive is that they put his name out there, they put the very, very strong statement first, right? Out of all the interviews, they put his face first, his statement first, right? And he had some sunburn, he's not in the best shape. So they were demoralizing that person, the guy, and they put his name out there. They put his name, okay? So how moral is that? If he's graduating soon, he may not be able to find a job because of that. If there was no name, at least, if the face was changed, the voice was changed, then that'll be fine. And that would still make the point that the college students are not listening, they don't care about the coronavirus. And even if they put exactly the same phrase, right? But they put his face there, they put his name there. And now when a company is about to hire him, they'll probably run a background check, and where is his name going to pop up? Good luck starting the career. So my question is, how moral, how sensitive is that? Because I know I know that making that point was not the purpose. The purpose is to get as many views as possible. How do you do that? You just like get the phrase out of the context. Okay, so like you need to create something like eye-catching. You need to create something which will draw attention. Because I remember I was giving interviews to TV as well. So they would, usually the way it goes is that they would ask you like that many questions, let's say 10, and then we'll just like cut it and edit, and we'll pull something out of the context, and hopefully that'll be like exactly what you meant. He might have been talking there for I don't know, 20 minutes, 10 minutes, and he might have said a huge amount of different stuff, but they pulled out like a very, very tiny, like one, I don't know, 3 sentences, and which completely demoralized him. And now he showed him from a horrible perspective. So my question would be to those people who are editing that, how sensitive is it? And how moral, how ethical is that? Anyway, lecture number 21, let's roll the intro. Hi guys, welcome to Computer Science 318, lecture number 21. Today we'll be talking about decrease by constant factor algorithms. I'm going to provide 2 algorithms. One of them is actually very well known to you. And no mind-blowing content to you guys. Today, everything will be safe, so don't worry about that. Anyway, so decrease by constant factor algorithm, what does that mean? That means we have a problem. Okay, let's jump to the slides. Not to the slides, but the document. So again, let's say that you have that big of a problem, right? Decrease by constant factor, that means you're going to divide that problem by some constant factor. So let's say by 2, okay, every time you go inside of recursion or iteration. So for example, the size of this problem is n, that becomes n over 2, okay? And then you solve that n over 2 problem, okay? And that kind of helps you to solve the whole problem. So the idea is that instead of just decrementing the size of the problem by 1, so it was n, then n minus 1, n minus 2, n minus 3, you're talking about n, then n over 2, n over 4, n over 8, n over 16, stuff like that. So you're decreasing by constant factor, which means you're dividing by that factor, let's say by 2. Okay, that's the most popular way of solving that, so dividing by 2. The first algorithm which we're going to discuss is something which you're very, very well familiar with, and that is binary search. Okay, so binary search. Keep in mind that starting from this week, you will need to submit the notes for all the lectures along with your homework. So that's why don't you take those notes right now? Okay, so what is that? It works by comparing a search key k with the arrays middle point, or like middle element a of m, right? So where m is the index of the element which is located right in the middle in the array. Okay, so first off, one of the prerequisites of the binary search, I really hope you remember that the array which you are looking within for a key, for an element, has to be sorted, either in decreasing or either in decreasing way or decreasing way, increasing way, decreasing order, doesn't matter. But it has to be sorted. It has to be like either go one way or the other way. The numbers always have to either increase or decrease, or at least have to be the same. That's okay sometimes. AM. Okay, so if they match, the algorithm stops. Otherwise, the same operation recursively repeats. And now recursively repeats for what? And that's where decrease and conquer. So like with the, decrease by constant factor. Okay, so that's what happens. So you repeat it, but you don't repeat it on the same size of the problem. The size of the problem decreases by a factor of 2. So you repeat it for the first half, if your k is less than a of m, or for the second, if your k is greater than a of m. Yeah, perfect. So it's either or. Okay, so kind of to remind you again how that works, let's say you have, so let's say that's your array. It is sorted in either increase in order, decrease in order, let's say increase in order, so the numbers actually just get bigger, bigger, and bigger. Okay, and let's say you're looking for an element, let's say that element is located somewhere over here. So what do? Like, you first off, you compare your key to the element which is right here in the middle, and let's say your element which you're looking for is less than the element in the middle. In this case, you're thinking like, okay, so all the elements to the right, then like they are definitely not the element I'm looking for, right? So let's say, for example, this is, I don't know, 10. You're looking for 10, and that's 500. Okay, since it is a 500, you're thinking, okay, so all the elements on the right have to be even greater than 500. That means it's definitely not 10. So I'm not going to even search in that right half. That's the idea. So that's what's yeah, and that's how we throw away the entire like half of the array. That's why we decrease the size of the problem by a factor of 2. Okay, perfect. Yeah, so that now come here. Next, what do we need to remember is we have array of 0, right? Then like bunch of a's, then array of m minus 1. So m is the middle index. Okay, then we have a of m, then we have a of m plus 1. Okay, and then we go up until a of n minus 1. Okay, so the total number of elements is n. Okay, so this guy a of m kind of symbolizes the element in the middle. So let's say the k is equal to 70, so we're looking for 70, and let's say our array is 3, 14, 27, 31, 39, 42, 55, 70, 74, 81, 85, 93, 98. Okay, sometimes I like, I guess, creating a little trick for my students. I'll show it to you in a second. I would create something like this, 20. Okay, so if I tell you, hey, like, please implement binary search for this particular array, what you should write in the quiz is that it's impossible. So that's like the input is invalid. That's incorrect. Why? Because this particular array is not sorted. This 20 is out of order. That should not be here. So the right answer would be like the binary search does not work for this particular array, because this particular array does not satisfy the biggest requirement of the binary search. Binary search, which is the array has to be sorted. Okay, but let's say we're looking for 70 in this particular array. Okay, so in the first iteration, okay, so let's say iteration number 1. Okay, our m will point at that 55. Okay, so that's our m. We're going to introduce 2 indices, left and right. So that's our L at the very beginning. That's our R. Okay, so what happens here is that, again, we're comparing 55, which is a of m, to our 70. So what do we know? We know that 55 is less than 70. That means we need to throw out the entire left half. Okay, what does that mean? We need to, in the next iteration, in the iteration number 2, we need to, so we throw away m, okay, and we throw away the entire left half, which means r has to be the same, and now L will be that 70, okay, and now m would be whatever's between this L and this R, which will point at 81. So this will be our, hold on. So this will be our m. Okay, so that's our L. So L points at 70, R points at 98, M points at 81. And again, we're looking for 70, right? We're looking for 70. Okay, in that case, what do we do? Oh yeah, well, first off, we have already thrown away this half. Okay, this 55, also useless. Okay, now we're comparing 70 to 81. What do? We throw away the right half. Okay, so we need to throw this away, including 81, right? Okay, so after that, what do? We don't change L. L is not changed. We change R to point at 74. That's our R. And where is our M? M is between 70 and 74. So basically, if you like find the middle between the two elements, it will be the first element, which means M would also be the 70. Okay, and then you compare an A of M, which is 70 to 70, and that's something which we're looking for. 70 is equal to 70. Boom, bingo. That's it. We're done. Okay, so that's iteration number 3. Okay, yeah, that's the binary search. Yeah, and then you return the index of 70. In this case, it will be 0, 1, 2, 3, 4, 5, 6, 7, 7. Okay, hope it makes sense. Now let's talk about the algorithm. What does it look like in the pseudocode? So binary search. Okay, we have an array from 0 up until n-1. We'll also have k. Okay, I'm not gonna put any comments here, but anyway, so L is equal to lowercase l is equal to 0. R is equal to n-1, right? So that's the left and right border at the very beginning. And then while L is less than or equal to R, okay? So while left index and right index don't overlap, because if they overlap, if they equal to each other, right? Or they overlap. No, if they overlap, that means we were not able to find the element, and now kind of like the difference between left and right border is nothing. Okay, so or like negative number, that means we're done. That means we're not able to find the element we're looking for. So while L is less than or equal to R, M is equal to, how do we find the middle between left and right? So we add them together, divided by 2. Over 2. Okay. If K is equal to A of M, then what? Then we'll return M, okay? Because we're looking for the index. If that's not the case, right? Else, if K is less than A of M, okay? So if the element we're looking for is less than the element in the middle, that means we need to go to the left. Well, I guess like to me it's left, but to you it's not left. Anyway, so we need to call the same function. It's a while loop. Okay, so now we don't change L, we just change R. We change R to n-1, right? Yeah. Else, so what's the only case left? K is not equal to A of M, is not less than A of M. So the only case left is when K is greater than A of M. Okay, so which means we do else, not else if, but just else. Else L, and we're changing L to n+1, right? And return -1. Okay, which means that if you never return M and you exit the loop because this is not true anymore, that means you were not able to find the K, your key, the element you were looking for, and in that case we come to this line where we return -1. Okay, so let's try to analyze this. So I don't know, basic operation, what would that be? Okay, yeah, so I guess what's the input size? The size of the array, right? Or what's the basic operation? The basic operation will be this comparison. How many times you compare your key, your K, to A of M. Now, does the number of the operations depend on the structure? The answer is yes. The answer is yes. Because if the element in the middle is immediately the key you're looking for, if k is immediately equal to a of m, that means you just do it on basic operation only once. If the element, if the key, if the element you're looking for doesn't exist in the array, that means you have to search for something which doesn't exist, and that will take you some longer. So that's why we'll only talk about the worst case scenario. What is the worst case scenario? It's exactly that. It's when the element doesn't exist in the entire array, or it's somewhere like on the basically. So let's say you have how to say that? So let's say you have 20 elements in the array, right? And then m would be equal to 10. Okay, if the element you're looking for is located at the m plus or minus 1, which means at the 9th or 11th position, that'll be basically the same thing. It will be like very, very close to, you have to do the same amount of comparisons as if that element didn't exist there at all. Anyway, so the worst case scenario is one of those two things, but let's say that the worst case scenario will be when the element doesn't exist in the entire array. Okay. So that's why we need to take care of only the worst case scenario. So C worst of n. Okay, so how many basic operations we will have to perform if we have, like in the worst case. Okay, so in this case we would have to, so keep in mind that when you're looking at something like this, right? So it's iteration, like while loop. While loop is similar to for loop. So you may be thinking then it's going to be n, right? So if you have two for loops, then it's going to be n squared, 3 for loops, n cubed. If I have like one for loop or like one while loop, that means it's going to be n. Not necessarily the case, and that's a vivid example. So don't rush to conclusions, don't rush there thinking that it's going to be big O of n. That's not true, and that's an example of that. Why it's not true? If you had an array and you were just consecutively like visiting each element, that would be n. But here, you're not visiting them, all of them. You're visiting like half, and then half of the half, half of the half of the half, half of the half, half of the half of the half of the half, and so on, right? It's not even close to visiting all of them. So that's why you visit only like a fraction. That's why it's going to be, the idea is like, so at the very, if we're talking about this for loop, right? What is the size of the original problem, n? What is the size of the problem after the first iteration? It's going to be n over 2 because you're going to throw away half of the array. What is the size of the problem after the second iteration? It will be n over 2, which was left, divided by 2 again, which will be like n over 4. Okay, so that's why the worst case scenario is going to be, see worst case scenario of n over 2 plus 1. Okay, so that's so-called recurrence in maths. When we define a function through a function but with a smaller argument, through the same function. Okay, and then if you solve it, and you can look it up in the book, it's going to be log base 2 of n plus 1, right? Yeah. And that's going to be, which is very similar to big O of log base 2 of n. Yeah. So log base 2 of n is less than n. That's why that's much more efficient than a linear search. A linear search algorithm is big O of n. Binary search is log base 2 of n. Okay. So it's not n over 2. No, it's log of n. Okay, hope it makes sense, but I'm pretty sure again you knew about the problem before. Next problem, fake coin problem. Fake coin problem. Okay, so among n identical looking coins, one is fake. With a balanced scale, we can compare any two sets of coins. The problem is to design an efficient algorithm for detecting the fake coin, and is a version of the problem. The one we discuss here. The fake coin is known to be lighter. Okay, so there is a more difficult version of the problem when you have, let's say, 9 coins, one of them is fake, but you don't really know if it's lighter or heavier. In this particular case, we're gonna assume that we know it's going to be lighter. Okay, that makes it like a bit easier. Okay, cool. So the question is how you solve it. You probably heard a lot of like jokes like that and problems like that over the internet. And again, it's like decreased by constant factor, right? Decreased by constant factor. So let's say you have like, I don't know, 20 coins, right? Or let's say you have like 8 coins. You split them into groups, 4 and 4. You weigh them on the scale. Okay, so let's say that shows you that it's lighter. Okay, so it goes like that. That means the fake coin is somewhere in this pile. Okay, so there are 4 coins. You split them into 2 groups. Okay, you weigh them as well. And let's say like this goes down, so that's lighter. So we have 2 coins here. That means one of them is fake. And then you just like, put 1 coin on each like side, and one of them like goes up. So that coin is fake. Same thing every time when you have like 2 piles, you put 2 piles on the scale. The one which is heavier, you definitely know that the fake coin is not there. So you completely throw it away, and that's how you decrease the problem, the size of the problem by 2. Yes. Okay. Yeah. So the idea is to divide n coins into 2 piles of n over 2. So the question is, of course, like what happens if there is an odd even number of coins, right? So that'll be like kind of the question to you. I don't want to answer that. Think about that. What happens if you have like 9 coins or 11? What do you do then? Yeah, so you divide them into 2 piles, okay? And now here's the answer: leaving 1 extra coin aside if n is odd. Okay. Put the 2 piles on the scale. If the piles weigh the same, the coin put aside is fake. Okay. Otherwise, we can proceed in the same manner with the lighter pile. Okay, that's it. So, well, okay. We'll let a pile which must contain the fake coin. Okay, so we can easily set up so-called, again, recurrence. So usually, yeah. Okay. Well, never mind. So the recurrence is going to look like this. Hope you know that from maths. So weight of n is weight of n over 2. Okay, plus 1. What does that mean? That means, so how much work do we need to do in order to, how much work do we need to perform in order to solve this problem for n coins? It's basically comprised of whatever it takes to solve the same problem for n over 2 coins, right? Plus 1. So that 1 is amount of work which it takes for you to compare. So like, what's the basic operation? The basic operation would be comparing like 2 piles, right? So that would be 1. So you like this account for 1 one basic operation, right? So whatever the amount of work you need to perform in order to solve this problem for n coins is equal to the amount of work you need to perform in order to solve the same problem for n over 2 coins plus one comparison. Okay, and now if you solve that mathematically, you would basically get to you basically get to this exactly the same. So that's exactly the same recurrence as here, right? Exactly the same recurrence. In this particular case, of course, the structure of the algorithm doesn't really depend on the number of basic operations, which is this comparison, doesn't depend on the structure of the input, right? So that's why there is no worst case scenario. So we have exactly the same recurrence. Again, it's solved exactly the same way, and the answer is also the same. Okay, which is big O of log n, log 2 of n. Yeah, that's it. Cool. Yeah, hope it makes sense. Now, there is interesting detail though, that this algorithm is not the most effective one. Okay, it does not provide the most effective solution. Okay, it would be more efficient if we divide the coins into 3 piles. Okay, about n over 3 each. Okay, so that's also another question I'll have for you. I'm not going to explain it now. How is it going to help? How is it going to make it more efficient? Please research that. I will be glad to ask that on a quiz. How does it help? How does it make it more efficient? If let's say I have like 8 coins, I divide that into, I don't know, 3, 3, and 2. Okay, how's that going to help? Okay, cool. Yeah, hope you guys enjoy that. I'll see you next time on Thursday. Have a good one. Bye bye.